Okay. Uh, so the hydration feature that I'm talking about today is what we call the 3 micron band. And so this is essentially uh, the asymmetric symmetric fundamental stretch transition absorption feature of the OH bond. And in a very similar area is also this first overtone of the H2O vibration band. And so this figure from Peters et al. 2009 on the left side of the slide shows how OH in the green, the orange water, and the blue water ice, this region in the around 3 microns has a number of absorption features. And so when we're talking about hydration, we're talking about a broad absorption feature here. It doesn't necessarily mean that there's molecular water there. It could just be entirely hydroxyl. And so I'll try and refer to it as the hydration feature throughout this talk. But as you'll see, we are suggesting that there might be both molecular water and hydroxyl there. So I want to talk a little bit about the Deep Impact mission, just since that's the spacecraft we got to use. Deep Impact was a mission led by Michael Ahern from the University of Maryland, and the goal of it was to study the composition of a comet. So this spacecraft went and essentially shot a 820-pound copper impactor into Tempel 1-9P and observed the result of that impact, what gas and dust compositions it threw up. So the spacecraft had 2 instruments aboard it for those sorts of observations, and they were both spectrometers, one high resolution, one mid resolution. But like many NASA missions, the spacecraft was well able to continue in its life, and so they did an extended mission, which was broadly called EPOXI, or Extrasolar Planet Observations and Deep Impact Extended Investigation, which was really 2 projects happening at once. But to get to the next comet they wanted to go observe, they needed to do gravity assists to change the spacecraft's path. And so during those, they took calibration observations and some science images that we ended up using of the moon during this time. And so the December 2007 and June 2009 gravity assists are presented in Sunshine et al. 2009, and the observations from December 2009 are presented in my 2022 paper. So as a little summary, if you're not familiar with Sunshine et al. 2009, they looked at these calibration and science images, and they found that the lunar surface has widespread evidence for hydration, this 3 micron band. And they found that this hydration strength varies with surface temperature, and they also found evidence for temporal variability of this hydration. And so, for example, from this figure from the paper, we can see in section C, Mare Imbrium is, there's a pretty strong band down to about 0.9, whereas at noon, it's a much weaker band, that one circled in the orange. I'm assuming you can't see my mouse. And so they saw this change in hydration strength with time, especially with a loss towards noon. So that's sort of the motivation for this work, is there's been evidence of this widespread hydration, variable with surface temperature and time of day. And so luckily for us, there was more data. This high resolution instrument infrared spectrometer, it goes from about 1 micron to just under 5 microns, which is really useful for the lunar surface because not only do we get the full extent of the 3 micron band, but we also get the thermal emission part. And so that enables us to be able to actually directly remove the thermal component. The saturation limit of this instrument, however, did limit the observations. We placed it at about 12,000 DN. And so what we ended up getting is we had 3 days of observations, and in this image, the green regions are where we were not able to do any analysis because the spectrometer saturated. This instrument was designed to look at a comet and not the moon, so the moon is a lot brighter, a lot closer to the sun, And the other thing is the resolution is not all that great in comparison to some of the instruments we have now orbiting the moon, like Chandrayaan-2's infrared spectrometer. But we were still able to get this pretty large scale view of the lunar surface. Improvements to the calibration pipeline occurred after Sunshine et al. 2009. So Klassen et al. 2013 updates the flat field and the bad pixel map and provides a correction for the pixel by pixel nonlinearity. And they had additional observations of the calibration star. And so all of that resulted in some improvements of these observations presented in Protopapa et al. 2017. And were incorporated into our work. You might be wondering, this data was taken in 2009. Why did it not come out until 2022? Part of that is that the mission found, in Klassen et al. 2013, found that the spectrometer's dark background needed to be adjusted through time. So there was a significant change from 2005 when we got to Temple 1 and 2009 when these lunar observations were taken. And unfortunately, for the third day of our data set, we didn't have skydark observations. So through a series of testing, we figured out that we could use essentially an in-scene dark, taking a dark part of one of the science observations and using that as our equivalent skydark. So we used the last 8 frames of the first science scan on the first day, which you'll see in the next slide, which we found was devoid of reflected light from the moon. And so there's some complications with using different darks, but essentially we scaled it in order to account for how the instrument's temperature varied on each observation day. So we were working with 9 lunar observations. They're all centered around the South Pole. The next slide will show the geometry of that a little bit better. But so this is the first 3 scans, the first day. And so the moon is in a slightly different location in each of these. The team wanted to ensure that as much of the surface that could be observed was observed. And so they pointed the spacecraft slightly differently to ensure that. On the first day, it doesn't really matter as much because the moon is pretty small, but on the third day, the lunar surface does take up the full length of the observation. These observations span 2 weeks with variable spatial resolution. So this first day is essentially the worst spatial resolution. It's about 70 kilometers per pixel. So here I've labeled some locations that might be of interest. And just as a reminder, these observations were taken essentially looking up at the South Pole. So we're actually seeing the moon rotate clockwise. You can see here that span in spatial resolution from 70 to 30 kilometers per pixel. One thing to note is we're taking about 2 weeks apart total. We do actually get some repeat regions observed on each day. And so, for example, there's a Mare that's observed around noon on the first day, and then observed in the evening on the second day. And then Apollo Crater is observed about mid-morning and then into mid-afternoon on the third day. And so what we actually end up with is a small region between Mare Orientale and Apollo Crater, which is observed on all 3 days, in the morning on day 1, in the afternoon on day 2, and in the evening on day 3. As I mentioned, some of the data did saturate, but what we were able to do in the process of our thermal model, our thermal removal model, which I'll explain in a second, is we went through and tried to save as much data as possible. So what we did was, if an individual pixel, spatial and spectral, reached that limit of saturation, then we essentially masked it. And then if greater than a quarter of the data in our thermal fit region was saturated, then we found that the thermal fit was unreliable and we couldn't analyze it. But we didn't have to totally exclude any pixel because some of the data was saturated. Removal of the thermal emission is really important around this 3 micron band and has been shown to be quite difficult for M cubed. Luckily, we didn't have that same level of a problem because our spectrometer goes out to about 4.5 microns. This is just an example of the data showing that even at some cooler temperatures on the moon, the thermal component is still really important and can strongly affect the data past 3 microns. And so even at higher temperatures, closer to that 390, 400 Kelvin, it's pretty significant longwards of 2.5, so affecting the 3 micron band. The method we employed was an iterative method to remove the thermal component. So we essentially walked through steps of assuming the emissivity to be 0.9 and then letting it vary until we found our best fit for the both thermal and scattered model. And then we used that to remove the thermal emission and change from our radiance over into apparent reflectance. One of the upsides, again, of this repeated observation is that we can test the results of this thermal removal. So this figure is showing the same location on the moon in morning, noon, and evening. And so we've taken the radiance data, which is all at different temperatures, and we've moved it into apparent reflectance using our thermal emission removal. And we find that these are very similar shapes and that the 3 micron band is still evident in these. And so that is pretty strong evidence that the variability in band depth is not just a result of our thermal correction or the observational geometry, but it's actually a real effect. Another thing to note, we'll get into the results in the next slide, is we majorly used integrated band depth as the measure of band strength here. And so how we did that is essentially it's a linear fit across the apparent reflectance around the band in order to remove the continuum. And then we took the area between 1 and that absorption band and integrated it to essentially provide this integrated band depth. And so we're not taking a singular measurement of what is the deepest part of the band, but what is the general area across the band. And so that accounts for the fact that this band is this asymmetric shape. So we have essentially 3 big findings. Unsurprisingly, we found that hydration is widespread and variable. It's been shown in a number of other works. We also found temperature and compositional dependence for this hydration strength. We found evidence for changes in the band shape, and we observed this diurnal trend. So this is a figure from my paper, and it's showing all of the data that we had separated out into Mare in blue and Highlands in red. And we can see that broadly the Highlands retain more hydration than the Mare do at lunar temperatures. And we also don't really observe much evidence for total loss of hydration. There's a couple pixels which do get to really low integrated band depth values. But as a reminder, our observations are really limited. So it's possible and probably likely that in the region where we've lost because of saturation of the instrument, that is likely where integrated band depths are very low or close to 0 or 0. So binning this temperature data into degrees of 5 Kelvin, or into bins of 5 Kelvin, we can see the trends a little bit more clearly. We can actually see that the Mare does have a higher integrated band depth, but only at the lowest surface temperatures that we observed. We also find that at the highest temperatures on the other end of it, that both Mare and Highlands have very similar integrated band depths, which is interesting. But more interesting than anything else is this change in slope of the integrated band depth with temperature. And so it's not happening at the same point between the 2 different compositions. There seems to be 2 different changes. We see this pretty quick loss of hydration strength in Mare up until about 290 Kelvin, at which point it slows down and seems to match the Highlands loss rate. And in the highlands, that's continual from the lowest temperatures we observed up until about 370 Kelvin, where that loss becomes fast. This is just another way to view that same sort of trend. So this is the Maria data binned into 10 Kelvin bins, and the whole band shape is shown. And so we can see that for the first 4, moving up from the lowest temperatures, these spectra are really spread out. And so we're seeing a lot of loss of hydration strength pretty quickly as we approach 290 Kelvin. For highlands, we see the same thing, but at the other end. At the highest temperatures, we see this really fast loss in band depth, whereas at lower temperatures, a lot of these bands are pretty squeezed together with similar band strengths. And so moving into the next thing we found that band shape seems to vary with temperature. Specifically, we found that band minima is shifted to longer wavelengths at lower temperatures. And so this figure here is showing 2 of those temperature bins, 360 to 370 Kelvin in the solid lines, and the dashed lines are 100 Kelvin below that at 260 to 270. Highlands again in red and Maria in blue. And you can kind of see it, it's a little bit difficult to discern here, but you can see that especially for the Maria, at lower temperatures, there is a shift closer, but not to this 3.15 micron absorption feature, which is more diagnostic of H2O. If we stretch this same data from 1 to 0, I've added these little yellowish arrows to point it out, we can see that shift in band center even more distinctly. And we see it much more for the Maria, which shifts from about 2.95 to 3.05, whereas the Highlands is a much smaller shift. Most excitingly, out of any of the results that we found, we got to look at the time of day dependence, thanks to this little repeat region. So on the right-hand side of the slide are 3 images of the moon. I've scaled them up just so that they match the size, but the resolution does change in them. And so we've got day 1, day 2, day 3. The blue and purple, the cyan and purple, are shown in the figure to the left. And this is the region that we have repeated. And so you'll notice it cuts off. It doesn't go all the way out to the limb. That's because of the saturation region on day 2. And so we limited it to just look at places where we observed fully on all 3 days. And so we can see broadly that there's 2 really noticeable trends. One, the decrease in hydration strength towards local noon, and then a recovery by evening. And then we can also see that more poleward latitudes have weaker variability. It's not super evidenced in this plot, but I did look into it, and also we can see the temperature dependence with those temperatures closer to 320 aren't really getting as low around noon as the integrated band depth values for temperatures around 360 to 380. Looking at just a subset, so now just those purple dots, we can see, again, morning and evening strengths are still similar, but evening is occasionally a little bit higher. And we can also see this evening recovery seems to have a temperature dependence. And so one thing I want to note on this data is it's not perfectly distanced from the terminator. So the morning observations that we have on day 1 are landing right around 7 hours into the lunar day, whereas the equivalent purple line on the right-hand side is for 17 hours or 1 hour before the terminator. And so all of the data is falling after that. So the evening data is closer to night side. So that is something to consider in our understanding of this data. But the interesting part is this really fast change in integrated band depth with temperature, especially in the evening side. And so I just wrote out some of our interpretations. Um, we found that Maria and highlands differ in hydration strength and loss rate, most likely related to the formation process of that hydration itself. We also found that band minima shifts at low temperatures, which suggests the contribution of molecular water. This isn't conclusive. Dreyer et al. 2010 found that the band minima can be shifted due to OH bonding with different materials. So we can't absolutely say that it's molecular water, but the band shift relation to temperature change suggests to us that it could be. And again, we find that there's this quick temperature dependent recovery. And so our interpretation of that is that it suggests localized migration of molecules, either OH and or H2O. Some previous work, Davidson and Hassani 2021, found that with surface roughness, water can be retained on the sunlit surface at any latitude and across all times of day if it's polewards of 45 degrees. And so our thinking is along the lines of shadows from roughness can provide these cooler regions, analogous but not quite the same as the micro cold traps described in Hain et al. 2021. Instead of being cold traps where they're trapped there, they're more of like cool spots where molecules can hang out for and survive a little bit longer. So these are the conclusions. I pretty much just went through them, so I won't rehash it too much, but I'll leave these up for questions and my favorite figure up for questions. And that's it.
All right, thank you. Do we have any questions already? I see clapping across several of the participants. So I'll go ahead and say a couple. I think they're more comments than questions, unfortunately, but I opened up the LAMP, the Hendricks et al. Data to see what temperature we saw the turn at. We were about 40 to 50 degrees north, not south. So different terrain. But we saw that happen at about 320, maybe 330 Kelvin. And I think you showed maybe a little bit colder was when there was that change in behavior.
Yeah, let me scroll back.
I'm curious if that's something you've thought about or have thoughts about if you're brave.
I don't know how brave I am. So the thinking that I have about this is that there's two different temperatures, right? There's this 290 and 370. And then looking at the band shape, I do think that the Mario might have some form of molecular water that's somehow able to stay on those grains up until 290, and at which point it's basically all lost. But I don't have a great, I'm familiar with the Hendricks paper. I don't know it as in depth as I probably should. So I'm not sure why there's that difference in the temperature ranges.
I guess you're at a little higher latitude than that paper, and Amanda's LPSC presentation, I think it was last year, showed that temperature shifting. No, it shifted colder. Okay, that doesn't solve it. Sorry.
It's okay. But that's definitely something I should look into.
We did have a question come in the chat. Menelaos Sarantos asks, how deep do we think we probe with these thermal measurements?
Yeah, so my understanding of this data is essentially when you're looking at the 1 to 5 micron, that's about as deep as you're getting. So these would be pretty superficial presence of OH and water, probably on between grains or on grains. But it's definitely not probing like really into the surface. It's the top level.
Well, I want to ask a related question on that. I mean, the temperatures that Mike was using and Mike and Amanda were using would have been from Diviner, but you're able to derive temperatures from your own spectroscopy at the same exact location. And so first of all, you're fitting the color of the longer wavelength end rather than the brightness, whereas the brightness temperature at, I believe it's 10 micron is what they're typically using with Diviner. So do you have any insight into what the emissivity is at the wavelength you're using? And then secondly, on that depth question that Menelaus was asking, there's also the question of how deep into the particles do you think you're probing for the amount of water that may be there? Because the absolute abundance of water is also of interest.
Okay, so on the first question about the Diviner data, sorry, could you, I'm just a little bit confused about what
Yeah, I got it messed up. Because you're fitting the shape of the spectrum and then also would have to fit the emissivity in order to have that work together to model that the spectrum. Do you have some insight on what value did you find for the emissivity at that 4 to 5 micron regime?
Yeah, so how we actually went through and did the thermal fit is we essentially started with an assumption of emissivity is 0.9, what temperature best fits our data from that, and then we allowed emissivity to vary. And through the end of it, we did like 4 steps through. We actually allowed emissivity to be wavelength dependent. So it's always below 1 and it's always near 0.9, but emissivity is expected to be wavelength dependent in this 3.5 to 4.5 micron region. So I don't have maps of it or anything like that, but I did also, from that same fit, we got temperature and we got emissivity.
Okay. And then the other question had been how deep into the skin of the material. So I'm saying material because of course the particles have surface roughness, but how deep into that skin do you think your spectra probe to evaluate the water in there that's hydrating it?
Yeah, that's a good question. I don't feel like I actually have a good answer to this. I will say, like, this is work I started as an undergraduate student and I'm still doing my PhD, so I'm not quite an expert. I think it's probably not very deep would be my guess, but I really don't have a good grasp on it conceptually.
I have another question. This is Carly. First of all, this is a fantastic analysis. I thoroughly enjoy it. A lot of great data, a lot of things to think about. One of the things that you got me thinking about was essentially the origin of the water. And this came up as you go through the cycle, how it's lost and then regained as the time of day. And you propose that it's mobile, that it gets lost, it hides and then it comes back. Can you distinguish between that and whether it's essentially lost, but then as it cools down, because it still has the hydrogen from the solar wind coming in, it basically reconstitutes itself? I can't really think of a way to distinguish which of those two models accounts for the coming and going.
Yeah, I think that's fair. I think it's really hard to differentiate between migrating and this, I think it's called reconstitutive absorption.
Recombinative, yeah.
Recombinative, sorry. I think it's really hard to distinguish between those two. I think potentially my thinking is basically if you look at this 3 micron band in regions of like short-term shadow, maybe that could alleviate some of the issue. So looking at like, okay, how strong is the band in morning shadow versus as soon as that surface gets sunlit again? But I'm not sure that that would conclusively prove either way.
Yeah, it's a good question, because one of the nice things, and I'm sure you're aware of this, is that when Trailblazer eventually launches and starts getting data, it has the advantage of having simultaneous measurements with a thermal instrument and a reflectance instrument. So it will allow direct measurement of the thermal component, and hopefully it will match the models.
Yeah.
But at least it will eliminate that variable or raise more questions that we haven't thought of yet. But it will be a really nice test for some of these hypotheses that we're all scratching our head about right now. Unfortunately, it doesn't have global coverage. It has to have only targeted coverage, just because it's a small mission. So we'll see. Hopefully it'll last long.
Yes.
All right, we have another one from the chat. This is from Phil Metzger. Do you have any thoughts on why the mineralogy of highlands forms or retains hydroxyl/water differently than the mineralogy of the mare?
It's a good question. I've talked with Alex Kling a little bit about it. I know he's on this call. I guess I don't have a super great idea of why it is, but I guess maybe if there's more like opportunities, I guess, for the solar wind to emplace this hydrogen to then create OH or H2O. Maybe Highlands has more of those. I'm trying to think of a word that I know I've talked to Alex about, but I can't think of the word. But yeah, sorry, that's not really a satisfying answer, but I don't really have a good idea.
I wonder if it might be a combination of kind of like what Menelaos brought up and Tim elaborated on, and could it be a spectral effect of the minerals and not actually a different composition? Could one of them be more transmissive to this wavelength range, and thus we can see more of the water that's in there?
That would be something interesting to look into.
And Phil followed up with, this is a fascinating finding. I think this will help guide laboratory experiments in the community.
Thanks.
Back to kind of what Carly was saying, if I can remember what I thought 2 minutes ago. It's been one of those kinds of days. Oh yeah, separating temperature and the solar inclination. This has been perplexing me for however long I've been doing this now. How do we do it at the moon? How do we separate because the sun is the main heat source on the moon, so they're correlated variables. And I think you had a couple plots on that, although I think you may have skipped that for time in the presentation. I saw it in your paper.
Oh, the incidence angle ones?
Yeah, the incidence angle plot.
Yeah, I didn't include that. I should have. Let's see if I can.
Now I can't find it in the paper either.
Oh, I know exactly where it is. There's too many things on my screen to escape. Yeah, so it was very interesting to me to look both at this temperature dependence, which seems really obvious and interesting, and then the incidence angle is sort of less of that. We still see this pretty steep drop-off in integrated band depth with lower incidence angles, so closer to that subsolar point. But the same patterns in temperature weren't as obvious. And so, yeah, I think there's something going on there where the surface temperature is more important than the incidence angle, but there's also the issue of the incidence angles we used were essentially assuming a smooth moon, whereas the temperature were actually derived from the observations. And so we're able to incorporate the complexities of shadowing and surface roughness without having to like model them. They're just, you know, real because they're in the data. The moon's not smooth. And so I think that maybe if you could look at genuine incidence angles per pixel that wasn't assuming the moon to be smooth, then maybe we could see more complex dependence on incidence angle for integrated band depth, but that's just not the data that we have here.
Yeah, and your pixels were plenty large to make it not realistic to account for those things.
Yes.
Unless you got a fancy model like some of the ones that you cited.
Mm-hmm. Yeah, so I don't think it would be possible to look at it with deep impact, but I think that Chandrayaan-2 you would be able to look at like localized shadowing with. The other thing, I didn't mention this, and I need to say it. So the data goes from like 30 kilometers per pixel to 70. So you might notice, you might not have, it depends on how closely you look at this, but the pixels on the left sometimes have two lines coming out of their equivalent like local noon. And that's because we've essentially doubled the pixels into the third one. I forgot to say that, and it's going to bug me if I don't tell you. So there's your reminder.
Right, because your pixels were so much better resolution towards the late day on this plot.
Yeah.
Okay.
That third day was a lot more fun to work with than my very blurry first day.
Yeah. Oh, we've got chat activity. Dave Blewett says or writes that the instance and phase angle dependence of integrated band depth would be interesting. And then Leslie Gersh writes, the mineralogy could also affect the surface roughness of particles and their size distribution in the wavelength range, though through mineral cleavage and fracture properties.
I think there's a lot of complexities to understand this correlation between surface temperature and integrated band depth. And I don't know that we can answer all of it through orbital spectroscopy.
Trying to think, integrated band depth is not, it's not a Hapke treatment. It's not taking account the roughness as I think you already stated.
Yeah.
So there's no like assumed particle size in these results. Here's what we saw.
Mm-hmm.
Okay.
Yeah, that's also partially why we don't have like the SPAT equivalent water. One, because we're not assuming that the 3 micron band is entirely water, but also because we were just like, we want to present, here's what we saw, here's the data, here's the band shape.
All right. Well, I just did what teachers taught me, which is count to 10 to see if anyone who is hesitant speaks up. So I think let's thank Kris again for sharing this work with us. And I know you're not working on this anymore, which makes me sad because there's a lot of follow-up ideas that have come up here, and a couple I think I had while reading the paper that maybe haven't come up here.
Yeah, I'm hoping the third project of my PhD, which I'm presenting at LPSC this year, come to my talk, is going to be focused on sort of modeling this idea of, okay, what happens to molecular water ballistically if the moon is smooth versus if it has the surface roughness. So moving a little bit away from spectroscopy into modeling, but I'd always love to come back and do more spectra.
So what smoothness rating or what when is your talk, I guess?
It is Thursday afternoon. I think it's at like
Oh,
3:50
that's right.
or something.
You're right after me or right before me. I forgot about that.
Yeah.
Yeah, okay. So that's in the one of the main Volatiles sessions on Thursday
Mhm.
afternoon. Okay.
Yeah.
Cool. Do we have another one of these before LPSC? It might even be canceled next month. So I guess now's your chance, people, if you've got to talk, especially if it's not in the volatile section. Here's a chance to kind of bring some attention to it.
I know Alex has a talk. I just don't remember when it is.
It's in the space weathering morning session, Tuesday morning.
Nice.
Cool. That's one. Another one I'm definitely trying to catch. All right. Any other walk-on topics? Did anybody who came in more recently happen to know the definitive times they're gonna launch and do these landing attempts on the moon?
I can plug one of the students I've been working with, Kira Wilk, who's giving a poster on Thursday where she's looked at various analog minerals and just recently looked at 2 lunar soils as a function of temperature and measured what happens in the character of the 3-micron band. And what's nice is it mirrors what you just discussed, which is great. So I encourage you to go to her poster and she would love to see you. Wilke, W-I-L-K-E.
Yeah, I got it. Yeah, thank you. That sounds super interesting. I'll definitely stop by.
All right, Zoom moved everything on me, but I don't think there's any other hands or anything up or any new chat. So I think we will go ahead and wrap it up a few minutes early. Oh, okay, now something came. Surface roughness and particle vesiculation strike me as important aspects for the ability of water to detach. Yeah, oh, sorry. That was from Tim Livingood.
Yeah, yeah, I see it. Yeah, I would agree. I feel like that's definitely an important thing.
Yeah, I hope I didn't miss anything super important the last few minutes. I had to take a phone call. But it couldn't have been important. I wasn't there.
Are you giving an LPSC talk?
Yes.
Oh.
Yes, I'll be doing one on the meridional variation of water as measured by neutron suppression, which is a touchy subject.
Okay.
All right, with that, I'm gonna stop this recording and